Okay, so here's what we were talking about last time. Well, this is the last theorem that we were talking about last time. Remember, we had set up this really strange construction, this new construction called the Hermitian Dot Product, right? Very weird thing. Because the old dot product just wasn't cutting it anymore, right? I mean, the old that old formula, multiply, add coordinates, was catastrophically unusable. Right? So, in order to be able to recover the kind of properties that would allow us to do meaningful algebra in a useful way, we kind of had to define this new thing that sort of forced us to come up with new ideas of what's an appropriate new concept of transpose, what's an appropriate new concept of symmetry. We defined all these other notions, not knowing at all what these things are useful for. Okay. So this was our first answer to that question. Why are these things useful? We get this very powerful conclusion. If you have a real and symmetric matrix, the eigenvalues are always real. It's a really weird, unexpected conclusion, and seemingly an intractably difficult thing to actually demonstrate. Okay. So proof ended up being a pretty straightforward application of this Hermitian dot product. You observe that this first step happens because the matrix, by being real and symmetric, is Hermitian. That's what Hermitian matrices can do. Make the observation that eigenvalues and eigenvectors, allow you to write that down. Recall that this construction, this Hermitian dot product that we were kind of forced into writing down just so that the algebra would work, has this feature that while scalars just factor out on the left, as usual, scalars on the right factor out with a conjugate. Let's just look at the formulas. That's just how it works. Right? And then the very nice conclusion is that this eigenvalue is its own conjugate and therefore must be real. So wonderfully convenient conclusion. What we didn't quite have time to get to is that knowing that the eigenvalues are real, it follows actually pretty quickly that what I'm going to loosely speaking say that the eigenvectors are real. But you'll notice what I wrote down here is that I can find a real basis for the vector space of eigenvectors. That's actually pretty easy to argue, and that is as follows. If you know that A was real to start off with, and then we just got through showing that the eigenvalues are real, that means that A minus lambda I is real. And how do we find a basis for your eigenvectors? Well, you just row reduce. You find the null space. And when you have a real matrix, the act of row reduction will keep it real. Right? Starts real, stays real. And solve for your pivot variables in terms of your free variables. There's no square roots anywhere in that process. So again, everything stays real and you get real eigenvectors. Okay. All right, so picking up from there. Next result, another really surprising fact. If you have a real symmetric matrix. By the way, don't forget that means that it's Hermitian. It means we can, move it from one side to the other in a Hermitian dot product. So, real symmetric matrix, we've already proved that these eigenvalues are real. What this new theorem says is that if you look at different eigenvalues and corresponding eigenvectors from those different eigenvalues, those eigenvectors are orthogonal. And I'm going to loosely say what this means is, in the way that you would think about this result, eigenvectors are orthogonal. Now, I just want to very briefly talk about what I mean by that. When I say the eigenvectors are orthogonal, I mean this eigenvector, for example, in that eigenspace, this eigenvector in that eigenspace. When we say orthogonal, I mean that these are orthogonal. What, of course, I don't mean, this would be silly, I am not suggesting that these two eigenvectors are orthogonal. Well, of course not. Right? So obviously they have to be from different eigenvalues. But since that is so obviously not what we're talking about, loosely speaking, it would be reasonable to say that real symmetric matrices have orthogonal eigenvectors. Interpreted in this obvious way. Okay. Okay, how do you prove this? Well, again, it's just a matter of playing clever games with these Hermitian dot products. So again, A is Hermitian. So it whips over to the other side in the Hermitian dot product in this expression. V1 is an eigenvector with eigenvalue lambda 1. V2 is an eigenvector, eigenvalue lambda 2. So we write that down. Factor out the scalars just as before. Lambda 1 factors out like that. Lambda 2 factors out like this. Now you're going to have this temptation, I hope anyway. I hope you'll have this temptation that when you factor out a constant from the right-hand side, don't forget to conjugate that. You should have an urge to conjugate this. After which you then realize, well, yeah, but I already know it's real, so I don't really have to write down the conjugate. Right, so no problem. Okay. Having done that, take this term, whip it over to the other side, like so. And then we observe that, as we assumed, because these are different eigenvalues, that means that this factor is not 0. We have a product that's 0, but that factor there isn't 0. And that means, you might say we just cancel that factor. And so punchline, orthogonal, as desired. How are we doing? Questions? Everybody good? Really surprising result. Right? What I find most mysterious about these kinds of arguments is that well, there's two things I find mysterious. One is we start assuming that we have real objects, real symmetric matrix. We prove that we get real results, namely real eigenvectors, real eigenvalues. But how do I prove that real gives me real? I do so by assuming that everything is complex and Hermitian and going through these arguments in the Hermitian Alice in Wonderland world and to come to the conclusion that in fact everything is real. Right? So said differently, in this case, we have a very counterintuitive, that's the wrong word. We have a very non-intuitive argument with these mysterious constructions, the Hermitian dot product and Hermitian matrices, etc., that give us a very geometrically familiar result, in this case orthogonality. Okay. All right. Okay, last thing I want to talk about real symmetric matrices is going to require a little bit of discussion. I have to define a term. I want to talk about similarity. Y'all, of course, recall what similarity means. Similarity means conjugation. Okay, similarity means change of basis. It means conjugation. Same thing. All right, but a conjugation. So what I want to talk about is a refinement of this idea of similarity. Similarity means, yeah, of course, there's some invertible matrix, and you can write this down in the algebra works. But what if we knew even more, that not only is there a conjugation, but what if there were a special conjugation? Not just any old invertible matrix. What if this were a special kind of invertible matrix? Then not only are the matrices similar, but they're similar in that special way. And so, for example, this matrix here, anything that I know about it describes the nature of the similarity between the two matrices. So let me give you an explicit example of what I'm talking about. I think this is a very plausible definition. Suppose we have two matrices are similar. Don't forget similar means conjugation. Right? Let's suppose that I were to know that not only can this be done, but furthermore, this can be done, this conjugation can be found by way of a very special matrix, a matrix that is orthogonal, let's just say. Then it doesn't really quite cut it to say that these matrices are similar. Yeah, sure, they're similar. That's true. That's only part of the statement. Not only are they similar, but they're similar by way of an orthogonal matrix or an orthonormal change of basis. So pretty reasonable term is to say not only are they similar, they are orthogonally similar. So this is a kind of a grammatical construction, grammatical pattern that you could really apply to lots of different adjectives. Any special feature that you might note about the matrix P very reasonably becomes an adverb describing the nature of the similarity. So I wrote an exam question years ago. It was a long time ago. I don't remember when it was. You can hunt through and find it if you want. Come to think of it, it might have been on a final exam, so it might not be in my list of midterms. But I'll tell you what the question was. It's a long time ago. The question was, I wrote down something kind of along these lines, except, so the question was, the punchline, what would it mean? I gave a definition of a kind of a matrix. I gave a definition of what it means to talk about a matrix to be a weird matrix. And then the question was, what should it mean for two matrices to be weirdly similar? Right? And all you had to do was write down exactly this, replacing this word orthogonal with the word weird. Same construction, same sort of motivation for the terminology. Okay. All right. Okay. Analogously, what does diagonalizable mean? Well, don't forget diagonalizable means that you can diagonalize by way of a change of basis. It's, again, it's a conjugation, it's a change of basis, but specifically with the conclusion being diagonal. So diagonalizability is really a statement about a conjugation. So again, anything special that you might note about the matrix that does this, for example, if you know that matrix is orthogonal, then it's not just true that the matrix is diagonalizable. This matrix is more than that. This matrix is orthogonally diagonalizable. And that's a mouthful. It's a lot of syllables, right? Orthogonally diagonalizable. A little bit of a tongue twister. Okay, that's what it means. Okay. So why am I spending time on this? It's because this is the punchline of the next theorem. This is the last theorem I'm going to talk about in this section. If you have a real symmetric matrix, it is, as described here, orthogonally diagonalizable. All right, so it's not just diagonalizable, it is orthogonally so. It can be done with an orthogonal matrix. Okay. Now, let me remind you what a lot of these things mean. What does diagonalizable mean? Okay, sure, we know diagonalizable means conjugate to a diagonal matrix, but we also know it practically, in terms of the bottom line. What does diagonalizable really mean? It means that you have no missing eigenvectors. You can find a full basis for Rn consisting exclusively of eigenvectors. Right? What would orthogonally diagonalizable mean? Well, orthogonally diagonalizable means that the P matrix, namely the change of basis matrix, is orthogonal, namely that all of the eigenvectors in this case are orthogonal. That part we actually already knew. We already knew that real symmetric matrices had orthogonal eigenvectors. We saw that on the previous page. Right? What is new about this result is that not only are the eigenvectors all orthogonal, furthermore, they're all there. There are no missing eigenvectors. And this is a new statement that we had not mentioned on the previous page. Refinement of the previous result. Okay. Proving this theorem is a little bit more than we really quite have time for in Math 216. It's not ultimately that big a deal. It's just got a lot of details in it, and we're not going to talk about it in this course. Okay. Nevertheless, I want you all to know these results. I think these are really big deal. Real symmetric matrices. By the way, real symmetric matrices come up all the time. Y'all remember in Math 212? Y'all remember in optimization talking about this thing called the Hermitian matrix. You remember that? It's part of the second derivative test. The matrix of second derivatives. Real and symmetric, always. Well, assuming the functions are appropriately regular. So that is a real symmetric matrix of which type we're discussing here. So Hessian matrices have real eigenvalues, real eigenvectors. The eigenvectors are orthogonal, and furthermore, the matrix is always orthogonally diagonalizable. There's never missing eigenvectors. That's a tremendous amount of conclusions about a very broad category of matrices. Okay. We are going to skip the next couple of things here, partly in the interest of time, but we're going to skip Schur's theorem. We're going to skip this page here on orthogonality there's a complex version of orthogonality called unitary, and we're just going to skip this discussion. We just don't have time for it this term, and it doesn't really go anywhere in the rest of this course. So that we're just not going to. So you're not responsible for the stuff on this page here. Okay. We're done with Chapter 9. Let me remind you, we're doing Chapter 5 for a long time, and then we jumped up to Chapter 9. Now we're back to Chapter 6. The reason we did that jump up to Chapter 9 is because I wanted to get all the linear algebra done, and now that we have all the linear algebra done, we are prepared to solve more differential equations. Let me remind you, larger scale structure of the course. We started with a bunch of linear algebra. Spent a bunch of time talking about linear algebra and vector spaces and independence and bases and dimension, about abstractions, seemingly not knowing where it was all going, why we have to know this stuff, and then we use those new tools to solve a huge category of differential equations in Chapter 4. Right? Tremendously big category of differential equations, very relevant to physics and engineering applications and that kind of thing. Not just one. It's a whole category of differential equations. Okay. So a lot of linear algebra, big punchline in solving differential equations. Well, then we went off and did more linear algebra. Right? And I hope it comes as no surprise. To justify, to give you a motivation for why should you care about the linear algebra that we just did, we're going to use that linear algebra to solve another very large category of differential equations. Okay. So they're called systems of first-order linear equations. Here's what they look like. System, because there's a bunch of equations. First order, because there's only first derivatives, no second derivatives or any higher derivatives. Well, that's nice, right? Fairly harmless looking, just first order derivatives. And linear, why these are linear? Well, we're going to find that just like every other instance where we've seen the word linear, hope you all remember this big concept, but when you see that word linear, what that means is somewhere involved in the situation there is a function that's intimately fundamental to what's going on in your context, and that function is a linear transformation. We're going to see that linear transformation very soon. It's on the next page. So we'll wait until we get there to see that. Okay. So what I mean by solving this system is suppose that these, what we call coefficient functions, are given. And suppose that these, what I'm going to loosely call right-hand side functions, are given. I'll come back and talk about why I like that terminology in a couple moments. And then I would like to find these functions, y1 through yn. How would I go about solving for these functions y1 through yn, which of course you also see here in various places? How would I find those y functions? Okay. Now, let me first point out something you can't do. Tempting, but not possible. How about we just solve these equations one at a time? Right? You want to find y1? Cool, we'll solve this equation here for y1. Having done that, we'll move on and find y2, et cetera, and they all look really simple. They're just first order, for crying out loud, so how hard could this be? Well, of course, here's why you can't do that. You can't solve this equation for y1 because this y1 that you're looking for, this y1 that you're looking for is simply not the only other unknown in this equation. In this equation, there is also that yn, for example. I don't know what that is yet. How can I solve for y1 if I don't even know all the other stuff involved in the equation? It's not a well-posed question. You can't solve for y1 until you know yn. And so you say, okay, fine, well, I'll come back to y1. We'll solve for yn by looking in this equation. We'll solve for yn. Let's see here. Yn is there and there. And okay, let's solve for yn. Well, of course, I'm sure you can see this coming. Now, we don't know y1. So I can't solve for y1 until I know yn. I can't solve for yn until I know y1. By the way, not to mention y2 and y3, etc., right? So we have a circularity thing here. We just cannot take these equations one at a time. These equations are unavoidably complicated, twisted up, and wrapped up inside of each other. The y1 equation has got y2s in it, and the y2s are in the y4 equation, and the y4 equation has y3s in it, and it's just a rat's nest of connections and interrelationships. You can't just pull them apart. Everybody see what's going on here? See why this is a hard problem, despite appearances. Again, you see that first order, and you think, how hard can it be? Okay. All right. So yeah, this is tough. Okay. A little bit of notation. It's going to take us a while to get to solving these, by the way. A little bit of notation. So all of those coefficient functions, we're going to assemble those into a matrix. Call that the matrix A. That's the coefficient matrix. All of these, what I've called right-hand side functions, let's assemble those into a vector like so. You'll see why momentarily. All of our unknowns that we're looking for, y1 through yn, let's assemble those into a vector. And having done that beautifully, okay, I guess it's fine. Having done that, this great big monstrous system turns into a single vector equation. This vector that you're looking for, coefficient matrix times the unknown vector plus the right-hand side vector. Now this is just notation. I mean, this is still representing the exact same hard system that we don't yet know how to solve. Everybody on board so far? Okay. A little bit of terminology. You may recall that this G, this thing that we call G, something kind of like that came up in Chapter 4 when we were solving differential equations. When it's 0 in Chapter 4, we called that a homogeneous equation. So likewise, we're going to call this a homogeneous system. Now, complaint, wait a minute, in Chapter 4, that thing that we called G was the right-hand side of the equation. That's not what's going on here. This is not the right-hand side of the equation, as I have it written here, right? So, okay, sure. Let me just observe, though, that I can take this equation and just kind of move one term over to the other side, and I get y prime minus ay x equals G. Right, so writing it in this way over here, it is the right-hand side. Right, so there is a pretty reasonable analogy there. Now you might say then, okay, well, if it makes so much sense to write it like this, why did I write it like this in the first place? There's some stuff that's going to come up down the road that we're not ready to quite see yet, but it does turn out that even though in some cases this is very much the right way to think about it, there are other situations, points of view by which this is really a pretty natural way to think about it too. So be prepared to think about it in both of these different ways. Neither one is the right way to do it. But anyway, so there's that. Y'all remember this term, initial value problem? An initial value problem is a differential equation combined with an initial condition. What an initial condition looks like in this case, here's the differential equation. There's what an initial condition looks like. That's what we call, that's what we call an initial value problem. The initial condition is just said, for some input value of x, what are the values that y takes at that value of x? Okay. All right. Just terminology, but by the way, a kind of familiar terminology. Again, we had an analogous concept in chapter 4. By the way, this pattern will continue. Notice we've already seen some pretty good analogies between what we're doing here in chapter 6 and what we saw in chapter 4. That's going to be a very apparent pattern as we go through chapter 6. So keep an eye out for that. I'll be commenting on that as we go. Okay, next thing. Big theorem. You may recall back in chapter 4, one of the first things we wrote down was what I like to call an existence and uniqueness theorem. Namely, under certain conditions on the differential equation, the initial value problem has a solution and the solution is unique. Right? So the same thing, as it turns out, works here in chapter 6 under certain conditions, and now that there's details here. How do you prove this? Well, you need for the coefficient functions and the right hand side functions all to be continuous. That's just how it turns out. But in that very routine set of circumstances, we have existence and uniqueness for initial value problems. Solution always exists. That solution is always unique. Okay. All right. You may recall in chapter 4 why we needed this is because weird stuff happens sometimes that you might, if you have a non-nice differential equation where these conditions were not satisfied, then terribly unexpected things happen, like multiple solutions to the same initial value problem. That gets weird. It messes. You can't do linear algebra when stuff like that's happening because we need to be able to say certain nice things about, given a condition, there's a corresponding solution. We need that to work out nicely to be able to view these as linear algebra problems. So this is a sort of foundational importance in how we're going to approach these questions. Okay. All right. By the way, for your consideration, pretty reasonable question to ask. Why is this an initial condition? How come we didn't include any derivatives in our description of an initial condition? In chapter 4 we did, right? So how come here you don't have to include any derivatives? And different points of view that you can take on that, but I think the best point of view is that this definition of an initial condition, that's what you can use to define an initial value problem that has an existence and uniqueness theorem. That's what it has to be to know that a solution always exists and to know that that solution is always unique. Right? We make that as a definition because that's the definition that gives us a nice answer that we wanted. That makes it a reasonable choice. Okay. All right. Okay. Reminder. It looks like we're doing a lot of calculus here, right? As it appeared to be in chapter 4 as well. Look, we're taking derivatives. We're looking at functions and derivatives and multiplications, plugging in values of x, bunch of equations. This got a very analysis kind of feel. It feels a lot like, Calc 2, except more so, perhaps, right? So we made this observation also in chapter 4. Chapter 4, you're taking a bunch of derivatives and looking at equations of, and functions and et cetera, et cetera. Seems like you're doing analysis. I remind you that one of the top takeaways that I want you to have for Math 216, we talked about this back in Chapter 4, is I want you to realize that Chapter 4 differential equations, they look cosmetically like analysis problems. They're really linear algebra problems, right? You should think of Chapter 4 differential equations as being about vector spaces of solutions of known dimension that we deal with by finding a basis, establishing that they're independent, that kind of thing, and representing them with their spans. These are all linear algebra concepts. Linear algebra are most of the tools that we actually used to draw conclusions about the solutions in Chapter 4. Right, so I claim that the same thing is going to happen here in Chapter 6, and you can see a lot of that here already. So again, it looks like a bunch of calculus, but if you look deeper, differential equation like this, the solutions are elements of this vector space. Now you just got to kind of, let's take a moment and just kind of stare at it for a moment. This thing I'm calling a vector space, the collection of all ordered n-tuples of continuously differentiable real-valued functions. This is a vector space. Good Chapter 2 problem, by the way. Prove that this is a vector space. It's not hard to do, right? Good exercise, though, so please give that a try. This is a vector space, so when I say we're looking for solutions, what we're really looking for is vectors in a vector space, just like in Chapter 4. Furthermore, what I'm looking for really is a subspace of that vector space. Now, how do I know it's a subspace? Well, because this equation is equivalent to this equation. There's that observation we made on the previous page. Two different ways to write the same equation. What we are then looking for is we are looking for the kernel of a linear transformation. Linear operator L, defined by that formula. Now there's another exercise. Confirm for yourself what I have it's circled in blue here is a linear transformation. Right? So, again, this is starting to sound pretty linear algebra, isn't it? Right? We are inside of a vector space looking at a linear transformation, trying to understand the kernel as a subspace of our original vector space. That's real linear algebra talk. So, anyway, keep this in mind. I mean, ultimately, the way why we're interested in this discussion about these differential equations, it's not that, I want you to know the mechanical process of how to, given this, how do you write down a list of functions? That's kind of the trivial part of this discussion. What's interesting is how the linear algebra plays in to using those solutions and seeing them in the bigger picture. Okay. Alrighty. Y'all may recall, in Chapter 4, we wrote down a theorem that looks like this. It was a different kind of differential equation, of course, but very early on in our discussion of Chapter 4, we observed that the set of solutions is a subspace that is, in fact, n-dimensional. Now, it's a different n here. Here, the matrix being n by n. That's the n that we're talking about. But in Chapter 4, there was a different n, but the point, there was this theorem that says the set of solutions is n-dimensional. Here, our set of solutions is n-dimensional. Now, in Chapter 4, we didn't prove this theorem because at that time we didn't have the appropriate tools, and I didn't want to get bogged down. The book has a proof in Chapter 4. It's all intricate and detailed and ultimately, I think, fairly opaque. But when we got into Chapter 5, define linear transformations, we had the tools necessary to write down what I think was a very powerful, quick, elegant proof that our vector space was n-dimensional. The same big idea works here. I'm going to outline this for y'all. I think it would be a fantastic exercise for you to see if you could fill in the details. Here's the big idea. We're going to define here a linear transformation from the vector space of solutions into the vector space of initial conditions, just like we did back in chapter 5, I guess it was. And let me tell you what this linear transformation is. The linear transformation is plug in x equals x naught. Right? You have a solution. You can just write down, okay, what are the initial conditions for that given solution? Plug in x equals x naught. Right? So that's easy to write down. Some things that you can check. One, you can check that this is a linear transformation. That's an exercise. Right? Here's another thing that you can check. This linear transformation is bijective. And it's bijective because of our existence and uniqueness theorem. Right? If you look back at what the existence and uniqueness theorem says, the existence and uniqueness theorem says for every initial condition, there is exactly one corresponding solution. Let me say that a little bit differently. For every output, there is exactly one corresponding input. That's what bijective means. Right? So what we have here is, you write down an easy formula for a linear transformation. Check that it's linear. Very short, very easy to do. Observe that it is bijective by the existence and uniqueness theorem. And all you got to do then is cite a theorem from chapter 5, which says that bijective linear transformations, the domain and target have the same dimension. Then you just have to look at your collection of initial conditions. It's Rn. An initial condition is literally a vector in Rn, in this case, which is clearly n-dimensional, and therefore the vector space of solutions is n-dimensional. Right? So that's the argument. Again, I've deliberately left some details out for you guys to fill in on your own. I think it'd be a fantastic exercise. I encourage you to take a whack at that. As usual, if you have any questions, ask me in office hours. Bring it up in discussion section. Go to the TA's office hours if you like. It's all good. Okay. A little bit of notation. This is not a big deal. Terminology first. We just observed that we have a subspace. Being that our solutions make a subspace, we can talk about a basis for that subspace of solutions. And just like we did in chapter 4, we're going to call that basis a fundamental set of solutions. It's just like in chapter 4. It's just terminology. Such a basis, then, is a list of vector-valued functions. It's a list of vectors. And you may recall, on several occasions in the past, we have found it convenient for various different reasons to take a list of vectors and make a matrix out of it. So when you do that here, why? What does this have to do with anything? We'll talk about that in a minute. But when you do that here, what you get is something called a fundamental solution matrix, or sometimes they call it a matrix of fundamental solution. Any combination of the words matrix, fundamental, and solutions gets the idea across. So anyway, it's just a little terminology, and I'll show you momentarily why this is handy sometimes. Okay. All right. Let's get our hands dirty. Here's one of those differential equations. This is a system, keep in mind. Reminder. Let me explicitly write out what this system is. Right? This is the system y1 prime equals 1y1 minus 3y2. y2 prime is negative 2y1 plus 2y2. Right? So this system here is the same as that matrix equation. Okay, so how are we going to solve this? I want to try to underscore the linear algebra aspect of this. So I'm going to start by pulling a couple of rabbits out of a hat. We'll talk later about where these rabbits come from. But I claim that is a solution. To be clear, what that means is if you take this vector valued function, if you take its derivative, if you multiply by that matrix, you will find that you get the same thing. Don't worry yet about where I got this from. More importantly, how are you going to perform this little magic trick in the future? Where are you going to find these? We'll talk about that later. Right now, I just want to observe, hey, sure enough, easily confirmed, that's a solution. Right? Okay, likewise, this is a solution. Plug it in over there, take its derivative, plug it in over here, multiply by the matrix. It works. Okay. Having done that, we are done with the calculus. Everything from here on down is all linear algebra. Here's how the important linear algebra stuff works. Actually, let me show you how dead in the water we would be if we didn't have the linear algebra. Where would we go from this? Minus linear algebra. Pretend like you don't know any linear algebra. Well, we found two solutions. Maybe there's more solutions. I don't know. Right? I'm out of rabbits. My hat is not functioning anymore. Right? Maybe there's more solutions. I don't know. Possibly. If I do, maybe I get lucky. I find some more solutions. I still don't know if that's all of them. I kind of don't know hardly anything if we don't have any linear algebra. Okay, back to linear algebra. Here's what you can do with the linear algebra. Remember, we have a two-dimensional vector space that we're trying to understand. That's what our set of solutions really is. It's a two-dimensional vector space. I have here two vectors in that two-dimensional vector space. Casual observation, they're clearly not parallel. Two non-parallel, non-zero vectors in a two-dimensional vector space must be independent. Now I have an independent pair of two vectors in a two-dimensional vector space. Dimension argument tells me that this is actually a basis. Knowing that it's a basis, everything in that whole entire two-dimensional set of solutions, every solution has got to be, therefore, a linear combination of those two solutions that I just found. So not only have I now used linear algebra to produce infinitely many solutions, but I furthermore have used dimension arguments to show that there are no more than the infinite solutions that I just found. Very powerful. All right. Alternative ways that you can write this down. Of course, you can also just, instead of writing down, hey, it's the span of this basis, you can also just write down and say, hey, that's a basis. Don't forget we say basis by fundamental set of solutions in this context. And then here's another way you can write this down. This is just kind of an observation, but this matrix obtained by making a matrix whose columns are those basis vectors, those being the columns then of this matrix M, the process of taking linear combinations of these fundamental solutions, well, that is then a linear combination of the columns of that matrix, namely, it's just MC. Right, so this is a very compact way to write the exact same thing. That's why this fundamental matrix is handy. It allows us to write that span up there as simply a matrix vector product. It's just a shorthand. It's kind of convenient. Whatever. Okay, everybody on board with that? Okay. Alrighty, so we've solved one. Again, the big point, linear algebra. Okay, let's talk about particular and homogeneous. I hope it comes as no surprise, but just like in Chapter 4, where you could find the whole general solution to a non-homogeneous equation by finding one particular solution and then adding in all of the homogeneous solutions. Same deal. same exact statement is true about these Chapter 6 differential equations. For highly analogous reasons. Right? And let me further remind you, when we got into Chapter 5, I made a talk about a further generalization of this. In fact, if you have any linear transformation from V to W, any vector space V, any vector space W, with that linear transformation, you could make appropriate definitions of what is a homogeneous equation, what is a non-homogeneous equation, what is a particular solution. You write down definitions, just exactly what you would think they are. And with all that written down, you can state and prove a theorem about general equals particular plus homogeneous. It works for any linear transformation. Right? So ultimately, in the big scheme of things, the reason this theorem works is because here we have a linear transformation T, which is computed as follows. T of y is y prime minus ay. So because this is a linear transformation, that's why this theorem works. So that's a good, nice point of view, I think. So hopefully no surprises. Okay, the last thing I want to talk about, we're not going to be able to finish this, but I do want to plant a thought in your minds, and that is about the Wronskian. Pretty reasonable question. Is there a Wronskian that would make sense in this context? Keep it in mind, we're no longer just talking about real valued functions or complex valued functions. Now we're talking about vector valued functions. The solution, each individual solution I'm looking at is a vector valued function. What do you get if you take a list of vector valued functions? Right? If I took a list of vector valued functions, if I kind of tried to copy what I did in Chapter 2, I'm going to take these vector valued functions, take a bunch of derivatives of these vector valued functions. That would give me a bunch of derivative vectors. And you have too much. You couldn't squeeze that all into one matrix. So you just can't use the old Wronskian. The Chapter 2 Wronskian does not make any sense here in Chapter 6. So we have this very nasty question before us of can we come up with something that plays a similar role? And it turns out that we're going to do even better than that. Not only am I going to come up with a Wronskian that works in Chapter 6, I'm going to give y'all a general construction that will allow you to create effectively something along the lines of a Wronskian in any vector space at all. Any vector space. So it will allow you to address this question. Is your list independent or dependent for any vector space? Let's see, how much time do I have? I have 2 minutes. Okay, let me get a little bit started here. We'll start off with an easy theorem. Y'all can totally prove this first part all on your own. No big deal. Suppose you have a linear transformation. Pretty much any linear transformation. Now, a little foreshadowing. We are later going to take advantage that this is a vector-valued linear transformation. The outputs are Euclidean vectors. That's going to be convenient later on. For right now, though, all that really matters is that we have a linear transformation. And I want you all to prove for yourselves that a dependent list of inputs gives rise to a dependent list of outputs. This is a direct proof. No big deal. The way you're going to do it is you're going to say, okay, well, if this input list is dependent, we've got a relation. Just write down that relation. Take that relation, plug it straight into the linear transformation, and use linearity. What will fall out into your lap is an explicit relation between these output vectors that proves that the outputs are dependent. So I want y'all to fill in the blanks. That's a very accessible problem. Of course, as always, if you get stuck, ask me after class, discussion section, office hours, all the usual options. And this is going to end up being the big tool that we'll use to define the Wronskian. Yeah, okay, that's a good stopping point. We will call it a day here. See y'all on Monday. Have a great weekend.